Okay, let's get started. Welcome, good afternoon, everyone. So, distinguished members of the committee, esteemed colleagues, honored guests, thank you for coming. Support of and here's Casten's defense of her doctoral dissertation. We've hydrogen burn from slowly accreting neutron stars. Before we open the proceedings, I'll brief walk through people who have done this before what to expect. So after introducing the candidate, I'll turn the floor to Sarah. She'll give about 40 minutes or so colloquium on her research that she's been doing. During that time, if you have a very short question in the nature of a clarification, you are most welcome to ask it, but I respectfully ask that if you have a longer, more substantive question, please wait until the end. There'll be ample time for questions afterwards, so save the easier questions till then. At the conclusion of the question and answer period, the public portion of the defense will end and the audience will be excused, and we'll go into a closed door session with members of the committee, Sarah. For people out of town during that time, there's a very nice courtyard there you can walk around in. If you head south that way, across the street, dodging construction, and go slightly east, that is towards your left, there's a driveway that leads into a parking lot. From there, you have access to the plant biology botanical gardens. Still a bit early in the season, but a fantastic place for a stroll. Highly recommend it. After the closed door session, then the committee, Sarah will be excused. The committee will go into conference briefly, and we'll call Sarah back in for the debrief, and then that will close out the defense. Afterwards, then, as soon as that's over, we'll very quickly set up, and there'll be a reception here with some refreshments. Okay, so. Great pleasure to introduce Sarah. It's not often grad students come in with the start of a thesis already in hand. Most of the time you have to, there's a few years spent looking for what to do. Sarah actually came having done some research with Todd Strohmeyer, formerly of NASA Goddard Space Flight Center. And during that time, she made a very interesting discovery. And so came in with some research already started. So we agreed that would be good to pursue it. And of course, when you make an observational discovery, you want to explain it. So Sarah will talk about there's a hypothesis to generate, and then you want to test it, you want to understand it. And as research goes, the more questions you ask, start to dig in a little bit deeper, you cover more and more, now led to a theoretical effort. So Sarah's dissertation has also been unusual in that it combined both an observational project and a modeling project, as you'll hear about. So Sarah's going to talk on her work now at the International Symposium on Nuclei and the Cosmos. She was also invited to join a working group on X-ray bursts that was hosted by the International Space Studies Institute that's out of Bern, Switzerland and Beijing, China. So she attended that. In addition to her research, she's an avid science communicator. She's been our coordinator for an organizer for Astronomy on Tap, which is where astronomers go out to local venues and give talks. She also maintains an active channel on TikTok that actually led to her also having film credits. So, anyway, so that, I'm going to turn the floor over to Sarah, and she's going to tell you about what she's been up to.
Thank you, Ed. That was a lovely introduction, and thank you all for being here. This really means a lot. The room's packed. Before I start, I want to take a minute and note that it's my great-grandmother's 98th birthday today. And so it's my honor to dedicate this talk to her. Okay, so as Ed mentioned, I will be talking to you today about hydrogen-triggered burst on neutron stars. So without further ado, I'll start with some background. Neutron stars form when massive stars collapse. They hold about 1.5 times the mass of our sun, all squished down to a small radius of about 12 kilometers. This is about the size of a major city. You may know I've overlaid the neutron star size over Lansing, and hopefully you may agree with me, Lansing's not very representative of what I mean by a major city. So, because it is my defense and some of my family is here, traveling from Texas, and I was born in Dallas, I have also taken the opportunity overlay of what I think is a better representative city of what I need as a major city for the size of a neutron star. So as an aside, I don't think Texas would claim a neutron star as their official state star because it's much too small. And everything is bigger there. However, despite how small it is, you pack an immense amount of mass in this small volume, making it the most dense visible object in our universe. This means that it holds densities that we are unable to replicate here on Earth in our laboratories. So the only way we can study fundamental physics at these extremes is in space, and in this case, a neutron star. Specifically, the types of neutron stars that I study are in low mass X-ray binaries. This means there's a neutron star as the primary and a low mass companion. Over time, as these two orbit each other, the companion star will overflow its Roche lobe. Some of the material will be stripped from the surface of the star and formed into an accretion disk around the neutron star. Zooming in a little closer to the center of the accretion disk, you can see the neutron star here. To give you a better sense of what the makeup is of a neutron star, it's primarily made up of the core and also the crust, with just a thin outer layer. However, this outer layer holds a lot of really interesting physics, and because of that, I want to take a cross-section out of the neutron star and really blow up that envelope to get you a better sense of what's happening in the envelope. So at the top, we have the surface of the star. This is blown up in log scale to give you a better sense of what's going on in the envelope. And at the bottom, we have the core. For the purposes of this talk, I will primarily be spending all my time just a few meters into the neutron star, where unstable hydrogen and helium burning will occur. Over time, as material falls on the surface of a neutron star, the temperature and the pressure will increase because as the material accumulates, the strong surface gravity of the neutron star will compress that material until eventually either hydrogen or helium will ignite, cause a thermonuclear runaway as an explosion that we call an X-ray burst. X-ray bursts typically release energies about 10 to the 39, 10 to the 40 Earths. They last about tens to hundreds of seconds and occur on the order of hours to days. These are the most common types of thermonuclear explosions that are observed in our galaxy, with over 120 confirmed galactic sources and over 7,000 bursts. Here are two examples of light curves of the most common types of X-ray bursts that we observe. The different cases here largely depend on the rate of accretion. In the top case, when the accretion rate is lower, you have a hydrogen-rich material that falls on the surface of the neutron star. It has enough time that the hydrogen will stably burn into helium before the helium ignites, and this will result in a helium-rich burst. If you increase the accretion rates so that not all the hydrogen has time to fully burn into helium before the helium ignites, you will instead get a mixed burst of hydrogen and helium. Both of these cases have something in common. They are both helium triggered. But you might take a second and imagine a case where the neutron star surface is cool enough so that its hydrogen-rich material falls on the surface of the star. It does not immediately stably burn into helium, and instead, a layer of hydrogen accumulates on the surface until the hydrogen ignites. In this case, we would have a hydrogen-triggered burst. This is still largely an open question, the hydrogen-triggered burst regime, and will be the focus of the rest of my talk today. I want to take you back to 2019 Neisser observed a period of active accretion from Sachs J1808. Sachs J1808 consists of a neutron star and a brown dwarf and a type 2-hour period, and it has been observed really extensively to date. I believe about 10 periods of active accretion have been observed quite extensively just from this source alone. This is one example of what a light curve looks like of a period of active accretion. You have the time in days, and the y-axis is the photon count rate. These spikes that you see are the X-ray bursts. Immediately, you might notice there's quite a difference between the first and the second one here. It turns out that this first one here is not unlike anything we had ever observed before. Typical X-ray bursts look more like the second bright burst, or AKA the helium-triggered burst. So this is new. This weak burst is about an order of magnitude fainter, and this is what we set out to understand. We searched through the archives and found one other instance of this from the same source that was observed by RxDE in 2005. And you notice that at the beginning of the period of active accretion, there's another one of these weak bursts, followed by 2 other bright bursts. The last bright burst here, unfortunately, the brightest part almost certainly got cut off because of instrument saturation. However, it probably would have looked more similar to the second one there, bright burst, if we had observed it all. Zooming in closer to the first weak burst from the 2019 light curve from Neisser, we can see the profile shape. Immediately, you might notice that this profile shape looks quite different than the more common types of X-ray bursts that we discussed earlier. Is it possible that this is a different regime? Is it that it is a hydrogen-triggered burst? Well, let's walk through it. The shape of these different X-ray bursts is largely due to the nuclear burning that's causing the burst. In the case of hydrogen, it will be burned via the CNO cycle. Probably been a while since you thought about the CNO cycle, and maybe even in your classes, you don't go as in depth as I think about it in my research. So I'd like to take a minute to explain it. And I'll get a big stick to do it. So traditionally, we start at carbon 12. The blue arrows going up indicate proton captures, or you can think of it as a hydrogen nucleus. The red arrows going down are beta plus decays. What's a beta plus decay? Thank you for asking. I will use this first reaction here as an example to help explain it. So first, you'll start with nitrogen 13 up here. The number of protons you have indicates which element you are. So the 7 protons is the nitrogen. The number that you have is the summation of the number of protons and neutrons that you have. So when you have a beta plus decay, you turn a proton into a neutron, which is why you then change the element to carbon. You're now at 6 protons. But because one of those protons converted into a neutron, your number stays the same. And then because of conservation of energy and charge, you also come out with a neutrino and positron. Great. Now that we're experts in that, we can continue on in the rest of the cycle. So as you make your way around the cycle, you notice this part here has an orange indicator showing that it's the slow part. And that's because nitrogen 14 has a smaller cross section relative to the other isotopes that are capturing protons. And it's the slowest part of this cycle. You then beta plus decay again into nitrogen 15. You capture another proton, and this green arrow here releases an alpha particle or a helium nucleus. This part of the cycle is incredibly temperature sensitive because each one of these, let me think. Okay, so each one of the proton captors is sensitive to temperature. So as you capture more protons, you release more energy. As you release energy, you increase the temperature, and that increases the rate at which you can capture protons. So as you increase the temperature, you increase your ability to go through this cycle, especially at this bottleneck point. But at some point, you increase the temperature so much, past about 8 times 10 to the 7, that you come into this regime called the hot CNO cycle. At this point, you're so effective at capturing protons that instead you're limited by these beta plus decays. One thing about beta plus decays is that for each isotope, it has a different set waiting time for how fast that decay will occur. This is measured experimentally, and for every isotope, it's different because it's dependent on the nuclear binding energy. So in this cycle here, the oxygen 14 and oxygen 15 are the slowest part of the cycle. Because they have set waiting times, it's not sensitive to the temperature, which means that this cycle here is temperature insensitive. But to put this all back into context to our X-ray burst, because the normal CNO cycle is highly temperature sensitive, you get this runaway effect causing the peak. And then at some point, you're hot enough that you move into this regime where you're no longer temperature sensitive, but you're still stably burning hydrogen. So looking at this profile, it's possible that if it is indeed a hydrogen triggered burst, this might be the nuclear burning that we're seeing. So now let's talk about some conditions that are required for hydrogen triggered bursts. There's a lot going on in this figure here, so I'll take a second to break it down. On the y-axis, we have temperature, increasing as you go up. On the x-axis, we have column density. This is the amount of material per unit area. You can think about it as if you're on the star, looking down a column. If that's confusing, you can also think of it as a proxy for pressure. So as you increase to the right, you're increasing in pressure and also your depth in the star. These solid lines here represent the accretion rates. At the bottom, we have the lowest or slowest accretion rate. And as you work your way up the ladder, you have the highest accretion rates. Let's say we have this accretion rate. As we continue to accrete material, your pressure and your temperature will increase until you reach the dotted dash lines here. At this point, the conditions are right for hydrogen ignition, or up here at higher accretion rates for helium ignition. From this figure, it's then clear to see for hydrogen ignition, we need lower accretion rates relative to helium ignition. If we take our observed accretion rate and compare it against some theoretical estimates, we can plot it here on the figures. First, in blue, our estimated accretion range from our observation. And then I'm also going to overlay some others, Fujimoto in yellow, Cumming in orange, and Cooper and Orion just slightly below our estimate. Overall, our results are fairly consistent with theoretical estimates for hydrogen ignition. Another condition that you need for hydrogen triggered burst is a relatively cool neutron star. This is my cool neutron star buddy. He has been with me in every single talk in my grad school. So for hydrogen ignition, you can see for the temperature, you need a lower temperature than you do for the helium. And this is because of what I talked about before. If your temperature is too hot, past this red dash line here, then you move into stable hydrogen burning. And in order to have a burst with that sharp peak that you see, need unstable burning to occur. And what's interesting about the specific source that we observed this weak burst from is that deep spectroscopic studies of stacked shades and light have shown that the core cools quite dramatically in quiescence, meaning that it's likely that the surface temperature is indeed cool enough. So hopefully at this point, I have convinced you that it's pretty likely for it being a hydrogen-triggered burst. But one thing I want to point out is that in my background, I mentioned we've observed over 7,000 of these bursts. But these are the only 2 cases that we know of where we see these weak bursts about an order of magnitude fainter than what we typically observe. So it's fair to ask the question at this point, why have we not observed very many of these? Is it that they're rare? Well, one thing I want to point out from the 2 observations that we do have is that both of these weak bursts happened really early on in the period of accretion. So if they are hydrogen-triggered bursts and need a cooler surface temperature and require a lower accretion rate, then it might make sense that these are confined to the early onset of the beginning of accretion, where these conditions would be met. After accretion continues, it heats up the envelope, and it won't be cool enough. Another thing to note here is if it's true that they're confined to the early onset of active accretion, that makes them quite difficult to observe. These events are very difficult to predict, and it might be that because we have not had many observations at the beginning of these periods of outbursts or of active accretion, it might just be that we have missed a lot of them because of the way we have been able to observe. Another thing to note, that if these are hydrogen-triggered bursts, they require the cooler surface temperatures to occur. This might be one way in the future, moving forward, to be able to set upper limits on the interior temperature of the neutron star. I am optimistic, though, that maybe in the future we will be able to observe more. Recently, there's been efforts of an optical monitoring campaign that specifically have been observing about 40 low-mass X-ray binary systems to identify these periods of active accretion and trigger X-ray observatories to look at them. This consists of 2 telescopes, the Los Cumbres Observatory in California and the Phelps Observatory in Australia. And actually, this effort is exactly how we were able to catch the 2019 period of active accretion from stacked shades to light. There's a lot going on in this plot, so as always, I'll walk you through it. In the x-axis, we have time. The y-axis, we have photon flux. This gray band here is the quiescent magnitude, or when it's quiet, in the optical. And then we'll start to see the blue points here rise up a bit drastically from the quiescent magnitude, followed by the yellow squares that are the UV observed by Swift, and then the red stars here at the end, which were observed by NICER, and it's the same light curve that I showed you earlier. The point of the optical monitoring system is that it seems to be that the UV lags behind the optical and the X-ray lags behind the UV. So we can use this to trigger our X-ray observatories to be able to hopefully observe more of the earlier parts of the periods of active accretion. So I've talked a lot now about the conditions for hydrogen-triggered bursts and the observations that we've seen. I want to take a second to pause and recap what I've said. The conditions that I've discussed for hydrogen-triggered bursts is a low accretion rate, a relatively cool neutron star surface temperature. It's possible that they might be confined to the early onset of active accretion, which may have been why we have missed many of these observations in the past and have only seen 2 so far. But I am hopeful that this optical monitoring of these specific low mass X-ray binaries will hopefully bring more observations of weak bursts. So as Ed mentioned, we have these really interesting results in the observations that we've seen. But now we can turn to theory and try to understand more the conditions that are required for these types of weak bursts to occur. So what do our simulations say? First, I want to pause and think about the questions that we might want to ask, that we might want to pursue to answer. The first one is what conditions are needed to reproduce the observed weak burst? It's important to note that at this stage, it's a first step. We're not trying to fit the burst, just kind of reproduce something similar to start to understand what we're seeing. So these simulated bursts need to, 1, be observable. We have observed these things, so they need to be able to be observable. 2, have a similar profile shape of a peak and this extended emission that we see that we can call a tail. The second question is, from observations, we are able to infer the type of nuclear burning that's occurring, but in our simulations, we are able to follow these detailed nuclear pathways and understand more about the burning that's occurring. So does the simulated nuclear burning match this hypothesis that we had of this normal CNO burning causing the peak and hot CNO burning causing the tail? To do this, I used MESA, which is a 1D stellar evolution code. And my setup, instead of having to simulate the entire neutron star, because the physics that I'm interested in is having only a few meters in the star, and there are a lot of uncertainties, say, with what the core is like and what it's made of, we can instead have an iron shell. In the shell, we still have the enclosed mass, temperature, we have the radius of the neutron star, and on top of that, we can accrete whatever we want on the iron layer. The point of the iron layer is just so it won't interact and have nuclear reactions with whatever we accrete on top of the star. So as a starting point, we can take the typical parameters of a neutron star, take the conditions that we've talked about required for a hydrogen-triggered burst, and start with an accretion of solar metallicity. What we get is a profile shape that looks like this. I'll pull up the observed bursts, compare the two. You can tell they're not quite similar. Not enough yet. One problem is, even if we take the peak luminosity from our simulated bursts, it's about 133 ergs per second. And compare that with the luminosity of our observed bursts, it's several orders of magnitude fainter, which isn't exactly a problem. The real problem is that this peak luminosity here is several orders of magnitude fainter than the accretion luminosity, which means we would never be able to observe this event if it happened in reality. So now, because if you recall, I related hydrogen burning to the CNO cycle, if we were able to enhance the amount of CNO that we have, we could enhance the amount of CNO nuclei that are available to capture protons that would increase the amount of energy generated in a shorter period of time. So what if, going from solar metallicity of about 0.02, what if we increase that order of magnitude to 0.2? Now we're getting something that looks a lot more similar to what we were able to observe. We have this sharp right in the peak and an extended emission to the tail. So if I do this over a range of different metallicities and stack all the bursts on top of each other, we get a figure that has a lot of information in it. And this is great because I will spend pretty much the rest of the talk breaking down this figure. Don't worry, I'll walk you through it. In the y-axis, we have our luminosity. In the x-axis, we have time. I'll note here, at this point, we break it into log scale because some of the bursts and the tails take a long time. At the bottom here, we have a metallicity of 0.01. All the way at the top, we have a metallicity of 0.3. We held hydrogen fixed at 0.7, and as the metallicity increased, we decreased the mass fraction of helium. And then the bullet points here are the overlaid observation of the 2019 NICER burst. So the first thing I want to point out is that we were able to produce observable hydrogen bursts this way, just increasing the metallicity in the accreted material that we pile on the surface of the star. This horizontal line here is the accretion luminosity, and what you see above it is most likely to be observed, or at least that we would have the capability to do it. Now I want to talk about the burst profile shape. Take you back to the same slide I showed earlier. We're starting to match here a sharp rise and a peak, and this extended emission here in the tail. At least when we go to elevated metallicity. So this first question that we had here has been addressed. We have some bursts that are observable, and we see some bursts with similar profile shapes of the peak and the tail. Now let's move on to the next question of nuclear burning. In our simulations, as I mentioned, we're able to track more of the detail of nuclear burning. So I'm going to step you through what it's like to be a computational theoretical astrophysicist. So when I run my simulations, what am I looking for to confirm that this is the CNO cycle that's going through to burn hydrogen to helium? Well, I mentioned this point here, this orange line is the bottleneck of what the normal CNO cycle. So when I see my hydrogen depleted, I should be able to go through this part quite quickly and then get a pile up at nitrogen 14 because this is its lowest point. As I increase the temperature and the time, then we'll start to see some of the nitrogen 14 move into oxygen 15. So here on the left, we have the luminosity on the x-axis and the time in the x-axis. The black line you see is the observed luminosity, the luminosity that's coming out of the surface. And the red line that's dashed is the nuclear luminosity. So any of the luminosity that's produced from the nuclear burn. I've taken out these two lines in time here to show you the mass fractions of some of the metals. If we had scaled it all the way up, you would see hydrogen at the top depleting. But in that, we start to see carbon-12 decreasing, piling up in that bottleneck that we discussed of nitrogen-14. And then later in time, we still have a large abundance of nitrogen-14, but it's starting to overcome that bottleneck and be converted into oxygen-15, just as we expected with our normal CNO cycle. As we get hotter, we transition into this hot CNO cycle. We made a prediction in our observations that this extended emission of the tail is the hot CNO. So let's see what our nuclear burning shows. Over here at this point, we've moved into the tail. And you can see there's a large max fraction pile of oxygen 14 and 15 here, which is the waiting point, the slowest point, the hot CNO cycle. So I think it's safe to say we've transitioned to hot CNO. So it looks like here, our prediction that we have of the normal CNO and the peak, the hot CNO and tail, seems to check out. So now, going back to our questions, congratulations, we've done it. You might think we're done now, There's actually some other interesting science that came out of our simulations that I want to briefly discuss. One is that we saw two different classes emerge from our simulations that we did of slow burst and fast burst. So if you notice that there are dashed lines here that I ignored earlier, I'm now going to talk about them. So the dashed lines here are what we call the slow burst, and the solid lines, moving up in metallicity, what we call the fast burst. Take you back to this plot, similar to what we discussed earlier, but take out two cases. A low metallicity case of 0.04 and a high metallicity case of 0.1. Again, we're still seeing the black line is the volumetric luminosity, so what you would observe coming out of the surface. And the red line here is the nuclear luminosity. So in the low metallicity case, I want to point out there's a little bit of a bump here, or an inflection. You might notice there's a huge difference in the high metallicity case of this huge spike here in the nuclear burning. It turns out that this is quite important. In the high metallicity case, you are increasing the amount of nuclear burning, and therefore the temperature is really increasing at the base of the layer where you have the nuclear burning occurring. This is vigorous enough to heat the nuclear layer, or the burning layer, so much that you then have a sharp temperature gradient, which launches a convective region. This convective region is brief, but it turns out to be very important in transporting heat from the base of the layer up and out of the star, helping contribute to a sharp rise in the peak. That's why as we increase in metallicity, you start to see a faster and sharper rise in the peak. The last thing I want to talk about is the discrepancy between the peak luminosity and the tail luminosity from our simulated burst in comparison with the goal points we observed first. The simulated burst that most closely matches the peak of the observed burst is our accretion with the metallicity max fraction of 0.2, whereas the tail of the burst most closely aligns with our simulation of the accreted material of 0.02. This is very interesting because the burst, peak, and the tail both depend on the amount of CNO abundance you have, but at different times. The peak depends on the amount of CNO that you have at the base of the layer, which is where you ignite, and the tail depends on the amount of CNO available after any emitting has occurred, such as the convection that we talked about. What we have done in our simulations has been a uniform increase of CNO as we increase the metallicity in the accreted material, which causes the tail to rise to a higher luminosity and also the tail luminosity to increase. But what if there's a way to increase the amount of CNO at the base of the layer without uniformly enhancing the CNO in the entire envelope? So I'm going to pull out my cool neutron star bug and take you into the envelope. And now you can imagine a case where we have hydrogen atoms and carbon atoms. Because a neutron star is so incredibly dense, it has really high surface temperatures. So the mass discrepancy between the hydrogen and the carbon atom is actually going to result in a really strong difference in how they feel the gravitational pull. So as these sink, the heavier carbon atoms will sink faster relative to the lighter hydrogen atoms. And this is called sedimentation. It's one way we could think about enhancing the amount of CNO that we have at the base of the layer without uniformly enhancing the amount of CNO in the entire envelope, so that we would get a sharper, brighter peak and not have to also increase the tail luminosity to more closely match our observation ratio of the peak and tail luminosity. Now I want to circle back to bring our theory back to observations. If we plot all of our ratios of the peak and tail luminosity versus the tail luminosity here, we get this line here. This is useful if we continue to observe more weak bursts and are able to get out the peak luminosity and tail luminosity of the observed burst, because anything above these points here points to some sort of stratification of enhanced CNO at the base of the layer instead of a uniform enhancement, which is where the dots show. And in fact, if I were to plot 2019 peak ratio of the luminosity, it would go so far off this plot here that it wouldn't show up. And so hopefully with more observation, that can help us understand more about this level of stratification or entrainment in reality in the neutron star envelopes. So I think it would be a good idea to include sedimentation in future simulations as a next step. And really, it would be more physically realistic than just ramping up the amount of metallicity in the donor star, because the metallicity that high of 0.2, 0.3 is probably not very physically realistic. And now we can move towards getting somewhere that's a little more realistic. But all of this was a very good first step to learn more about the conditions for hydrogen triggered bursts. Want to recap the conditions for hydrogen trigger bursts that I've discussed? You need a low accretion rate, a relatively cool neutron star surface temperature. It's possible that they might be confined to the early onset of active accretion, making them difficult to have observed them in the past. But hopefully, with optical monitoring, we can begin to trigger in the optical so that X-ray observatories are able to observe this period of active accretion starting on the early onsets. And maybe that will mean we can increase our sample of weak bursts. On the simulation side, it's likely that you need enhanced metallicity to get observation or to get bursts that are observable. We were also able to reproduce the observed profile shape. We saw in our nuclear burning that normal CNO burning in the peak, and there was hot CNO burning in the tail. We also learned that enhanced metallicity leads to convection, which is quite important for transferring heat up to the surface and causing a sharper rise in the peak. And lastly, we discussed that there is still a discrepancy between the peak luminosity and the tail luminosity, and this might point to other physical processes that we've discussed, like sedimentation. And that moves me into the future work. On the observational side, I don't think it's a surprise to you that I'm hoping we can increase the sample size of the amount of weak bursts we have. This will allow for better constraints on weak bursts and hopefully convince us further that what we're seeing is indeed a hydrogen trigger burst. On the simulation side, I've discussed including sedimentation. We could also think about including ashes from previous bursts and the previous period of active accretion. And lastly, maybe including time-dependent accretion. If these weak bursts truly are confined to the early onset of this period of accretion, the accretion rate is likely still ramping up. So this might be another thing we can do to make our simulations a bit more realistic. So at this point, this concludes the full research presentation, and I'd like to move into some acknowledgements. Firstly, I'd like to thank my advisor, Ed. You have been so amazing to me, being flexible with me coming in with a project and allowing me to pursue that in my interest, and just always being there for me. When I first came in, I was less secure in my abilities to do physics, and he has turned me into a theorist. I also like to thank Several other people I really think of as my mentors and secondary advisors. Andrew, Todd, and Duncan have all been there for me in different ways, from theory to observation, helping me straddle the line of something that's quite difficult to both be an observer and to be on the theory side. I'd like to thank my committee. I appreciate that all of you were able to make it to the talk today, and the guidance that you've given me in the different committee meetings that we've had. And even if you're here for my 7-year project, I really appreciate all of that time and the advice that you've given me. This is my last slide, so I'll let you take a minute to sink it in, or to let it sink in, while I acknowledge a few more people. I want to thank my family who's here, who's traveled a long way to be here to support me. Specifically, I don't get emotional, my mom and dad, who have encouraged me and supported me and has always encouraged me to be curious, and is likely the reason that I am a scientist today. Sorry, take a second. My mom and dad also sacrificed valuable time together when it was my 2nd year and my health problems started getting worse. My mom moved in with me, helped me go through my classes in my master's portion, helped me get through surgery and recover from surgery. And I likely wouldn't be here on this date defending without that. I knew this was going to be hard, but now that I'm up here. Okay. I also want to take a minute to thank Michael. You have been really great, especially through this last year, which has brought a lot of challenges in unexpected ways. And I really appreciate your support. Okay, that's all. Actually, it's not all. I have one more. I want to also thank all of the grad students, because my time here, of course, would not be the same without you all. You have made it worthwhile to be here as a grad student. I love that we have spent a lot of time hanging out together, playing games. We always encourage each other and support each other. And I really appreciate every single one of you. Okay, that's all. Cry.
Okay, we're going to move into the question and answer part of the session. So they're welcome to raise their hand. For those online, I am monitoring the participant list. So if you want to ask a question, raise your hand and I'll recognize you as soon as I can. But the floor is open for questions. And so there, then Joey.
Back there.
Yep.
Okay. I'll start off our hard bit of crying to asking science questions.
Great.
Can you show the slide, the figure you have with the different simulated bursts and your observed burst plotted over it? So you talked about the peak and the tail. I'm wondering about the rise. Is there physics in the rise being different, or is it like a numerical thing? You had like dump all the energy all at once.
Of the observed burst or the simulated burst?
The simulated burst, like there's a mismatch between the ride and well, I'm here to get like interpret that, or if it's like a numerical.
Yeah, I think that has to do with the amount of CNO that you have and how vigorously you're burning. So when you have more CNO, higher catalyticity, and you're going to release more energy in a shorter period of time, which then causes this convective region, and with more metallicity, then you'll have a sharper temperature gradient and maybe more vigorous mixing or more heat that's able to be transferred to the surface, causing a sharper peak. I know you're not asking about the observation, but in reality, there would actually be like flame spreading that we have to take into account. We have an emission, it takes some period of time for it to fully spread over the entire surface of the star. So that's also something that's a little different that is not accounted for in our simulation.
No, I think I'm really curious about how we can sort of test your simulations observation. So I'm wondering what actually sets that metallicity that's so important for the morphology of the Earth. Is it something that's intrinsic to the neutron star, or is it like the metallicity of the accreted material from the donor?
Well, this is exactly what we're trying to probe, right? And so this is our first step. It's just uniformly enhance the CNO. This is simulating as if the accreted material from the donor star is different. So all the way from, a metallicity of 0.01 to the highest of 0.3. In reality, as I mentioned, this probably isn't physical to have a star that's 70% hydrogen and 30% metals and no helium. So we can start to think about what might be physically more realistic. And that would be like the sedimentation that I talked about. It could be the previous period of active accretion had bursts that left ashes that are now perhaps deeper star. Things like this would be more realistic. Does that answer your question?
Yeah.
Good.
So I thought this was excellent.
Thank you.
And as a planetary person, I did an absolutely fantastic job explaining a lot of this complicated stuff. The observer in me has a question. So it showed the nicer data 2019 and then look up to 2005. I had it backwards.
No, that's right.
And then each of those showing peaks. So my question here is more of an instrumentation question, is what I'm looking at this, which is, are the counts on the left and right the equivalent to each other?
Like
And, like, if this was like magnitudes, would they be scaled correctly that the peak of the week where you see is equating to the peak that you see on the graph? Or are they different in height?
They're different. Yeah. So the RSCE one was slightly brighter than the nicer one. The reason why I talked so much in detail about the nicer one is because nicer has a higher spectral time resolution. So because bursts happen on such a short time scale, it's nicer is really good for this. That answer your question?
We can read this as an absolute scale.
I think so. I know they scale with luminosity, so they should scale also similarly magnitude, maybe like loss or something. Yeah.
Reserve. Okay. Then you. Back there.
Thanks, that was awesome. I had a question about the sort of like nuclear burning side of things. And I guess I was thinking about this mostly like as an analogy to massive star cores, and that's the way that I would think about the CNO cycle. And I guess my question is, why do we never, or why is it not important for your research to like also have the like proton-proton capture process for low mass stars? Why it seems like it gets neglected and it's fine. I guess I was curious why you just like step over that stage, like building.
I am actually so glad you asked this because I have this backup slide. And I've never used it before.
Wow.
So this is where the PP chain dominates. Like the different types of nuclear burning that you have has to do with your density and your pressure. And so the regime that we are in is very much the CNO cycle. And normally your surface temperature of the neutron star is hot enough, you'll be stably burning, but in the cases that I was talking about, the CNO cycle was the normal one because our surface temperature was probably a little cooler.
Reserve. Do you have a question?
Yes, I do.
Okay, and then behind next. Go ahead.
Hi, Sarah, great job. I have a question also about the NICER and RXT light curves. So you have all these amazing conclusions about the weak, the very short events that you've observing, but it also looks like there's kind of an underlying trend in the light curve, ignoring the weak and bright outbursts. Kind of it comes up, it kind of wavers for a second, then it decreases, kind of in both those on a period of a couple of weeks. Can we learn anything about the environment on the surface of the neutron star from that underlying trend? It might be outside your wheelhouse there. Just curious.
About the neutron star surface specifically? I'm not sure about during the period of active accretion. I know there's a lot of research that follows the cooling of neutron stars after the period of active accretion, and that tells you some information about the crust. As far as in it, I'm not sure.
Okay, thank you. I was just curious.
The other question.
Yeah, so like you were talking about this figure earlier, I think from Rebecca's question, but it's the one that compares the theoretical simulations to the observations. My impression earlier on the talk was that the L accretion horizontal line is kind of a proxy for what we can observe, but I can see that in the 2019 NICER burst, some of the observed points kind of dip below that 10 to the 36 ergs per second, so I was just wondering like, what exactly should I be thinking about, like?
Yeah, no, that's a good question. So the horizontal line there is the accreted luminosity. For to like get an observation, you need a high enough signal to noise ratio to be confident that you're observing, something different than the accretion luminosity. In this case, with the 2019 NICER burst, we were able to be confident that we observed something like an X-ray burst. And when you're confident in that, you can then subtract the persistent emission, which is like, as your material falls in the star, that keeps it up. You can take that and subtract it, and that's how you get the burst.
Yes.
I guess I was interested in what you said, like early at the very beginning about the companion to this neutron star being a brown dwarf. I wonder if you have any thoughts on like how relevant the structure of the brown dwarf is to this phenomenon, like it being a degenerate companion. Might that have changed if it was like a one solar mass star? Like, would we? I guess. What are your thoughts on that? Again, perfectly fine.
Yeah. So I guess brown dwarfs are a little out of my wheelhouse, but my intuition would say you're only stripping the outermost part of it, and you will at some point have like a gradient where you have a more idealized type of gas before you get to degenerate. I might not be saying the right thing. You probably have to ask Noah for sure, but my idea is that probably like fairly similar, as long as you have similar compositions. That would just be my guess.
Devin.
Yeah, I was just curious, very impressive work doing these one-dimensional models. There's lots of information there, but I'm curious what the implications are for the sort of much considerably more expensive three-dimensional work that's sort of happening.
Yeah, there's been some effort to do multi-D simulations of the flame spreading that I discussed, where like we don't include this in our simulations at all, but if you like how an emission at some point in the star, it takes some time for it to fully spread, and that will influence your observations. So there's been some efforts to do that. It's quite computationally expensive and takes a really long time. I can't remember how long they've been able to simulate it so far, but it's really just like seconds, like a few seconds, not even close to like simulating the entire burst at all. Yeah, I think the future of multi-D modeling with this is very interesting.
Okay, I'm going to start. But first, this question is starting to wind down. We're getting towards probably the end of this period. Last call in the back.
So for your base model, do you have any sort of base heating?
Yes. You do put in a base luminosity, which is like the luminosity or heat coming from the interior of the star. This is very important in studying also the cooler surface temperature that you need. So yes, that was an important factor in our models.
Was there any, do you have any specifics to this where maybe you had a different choice of mixing level? Or
Yeah. So I think we just use the standard mixing link in this case. I know we tried to implement different types of mixing, and some of them we found to be a bit unstable, which is why we chose what we did. And then we just made it consistent for all of our bursts. So yeah, there might be some work looking into the stability of different types of mixing.
Okay, I think if. So you pause on, do you have one question? All right, that's the last one. Go ahead.
So say in your model, you had a layer of iron over the surface. How reasonable of an assumption is that to make? I don't know what neutron stars.
Yeah, I think it's pretty reasonable because your most typical type of X-ray burst is the helium triggered burst. And what I didn't really mention is I didn't really go into the details of any of the nuclear burning that's happening in the helium triggered cases. The most common type is the mixed hydrogen helium burning. And in that, you not only have triple burning, which is the helium, we also have our key process happening, which is the rapid proton capture that goes all the way up to the iron peak. So it is realistic to have a layer of iron there. Mostly we were using the iron layer because it allowed us to accrete material and that wouldn't interact with what we accreted on it. But yeah, I would say it's somewhat realistic.
Okay, with that, I'd like to close out the session. Thanks, Sierra.